Hey, AP Chemsters, this is Mrs. Vanderwall, bringing you a new edition of the Blank Wall series. So today we're going to introduce to you Chapter 16, which is all about spontaneity, entropy, and free energy. And this is really the second part of thermodynamics, where when we talk about enthalpy and delta H, that was really the first part. And now we're going to continue, and delta H is going to show up again in this chapter. So let's first of all begin with section 16.1, which is the spontaneous processes and entropy. I sure hope you watched the crash course with Hank there, and I thought that he did a nice job talking about entropy as well, but we're going to use this in our notes. So there's the first law: energy can either be created or destroyed. We talked about that with delta H. And then we talk about the spontaneous process. And we have kind of like a misnomer. What does it mean to be spontaneous? It's not necessarily quick, like he described the getting your lip pierced in a mall or something like that. That's not necessarily what we're talking about. What we're talking about here is processes that occur without outside intervention, but we have no idea how fast or how slow they really go. We know that the Earth makes diamonds spontaneously, but it takes millions of years to do that. So we are not talking how fast, we're just talking that it goes without any additional energy from the outside, from the surroundings. So anyway, what is entropy? What does this have to do with anything? Entropy is the idea here, and I found a cartoon that I kind of liked. It helped describe entropy. Obviously, the word entropy starts off nice and neat, and it ends up getting kind of messed up. And that's the idea of what entropy is. Now, to give you kind of a background of entropy, I dug up the first guy. He was Rudolf Clausius, or Clausius. We talked about him with the Clausius-Clapeyron equation earlier, and it's the same guy here. And he was the first one to actually come up with the word entropy. He got it from the Greek word, I can't pronounce it, but basically the trope part of it. And the Greek of trope means a transformation. And so as you go back and think about that picture I showed you with the word entropy, there is a transformation. It's going from order to disorder. Now there seems to be some interest in why did Clausius call entropy S? And the best guess that people can come up with is named after the Sadi Carnot. And Carnot was actually a very young man. He went to a Paris school called the Pyrotechnic School. So you think he's going to do some fireworks, but it actually was the engineering and mathematical school. And same place where Gay-Lussac went from the gas laws. Anyway, Sadi was also in the military, as this picture shows, and from there he learned some about cannons and heat flows, and he started thinking more and more about steam engines. And so you may have heard of the Carnot cycle. I'm not an expert on him, but anyway, they think that Clausius named entropy after Sadi here. There's not an old picture of poor Sadi here. He died at age 36 from a cholera epidemic, as I just read, and so there's not a whole lot of pictures of him around except for this one. So that's Mr. Sadi. Well, back to our entropy, though. Let's go back to the other page. So what was Clausius doing? He called this idea of entropy a measure of randomness or disorder. And so like Hank said in the crash course thing, you know, if you clean up your room, you're disturbing the law of the universe here, where you're actually making your room neater, and that doesn't work. It takes energy to do that. I like to think of that too, and I'm cleaning my house, but I still clean it. It's also the driving force for a spontaneous process is the increase in entropy of the universe. So let's think about this. There are some things out there that, why do they happen? So for example, why does a ball roll downhill but never spontaneously rolls back uphill? If exposed air and moisture still rust spontaneously. However, the iron oxide and rust does not spontaneously change back into iron, metal, and oxygen gas. It's not reversible, is it? Why does a gas fill its container uniformly? It never spontaneously collects at one end of the container. Well, that's interesting. Heat flows always from hot object to a colder one. The reverse process never occurs spontaneously. Wood burns spontaneously in an exothermic reaction to form carbon dioxide and water, but wood is not formed when carbon dioxide and water are heated together. At temperatures below 0 degrees, water spontaneously freezes, but temperatures above 0 degrees, see, ice spontaneously melts. So it all has to do with this idea of disorder, spontaneity, entropy. So let's turn to the next page. And this idea is actually very important. Entropy is the thermodynamic, which is again heat, moving heat function, describing the number of arrangements that are available to a system. This is something you got to think about. And if you would like to, this is also all the diagrams are in your book on page 752 and 753. These are just some of them. So nature proceeds towards states that has the highest probabilities of existing. And so going back to why would a gas fill an entire container versus ends up at one end? If you have to look at how many different probabilities do you have, let's say we have 4 gas molecules, is it a high probability they all end up here? Is it a little better probability that 3 of them are on the left side and 1 of them on the right side? Is it a higher probability yet where you have 2 and 2? And that's really the answer. It's how many different probabilities do you have, and which is your most common one is the one that is most disorderly. So that's why a container fills everything up. The positional entropy is what we're going to spend more time with. This is what really deals with chemistry more. It refers to the entropy associated with the states of matter. So this is what we got to be thinking of. The probability of occurrence of a particular state depends on the number of ways, the microstates, we're talking about the molecules, in which the arrangement can be achieved. And actually, I would like to add something in here as well. All right, the probability of occurring, the solid is the most orderly arrangement possible. So here is my nice, neat little solid here. Very little bit of randomness. So there is very little disorder here. Now, if I have a liquid, here's my beaker, and there's a little bit more pathways for them to move around. They have a greater area of movement. The molecules are free to move around as long as they stay in the confines of this beaker. Now, in an aqueous situation, not only do we have the water molecules zooming around, but we have some other species in here as well, like maybe my sodium chloride or my sugar. So there is actually more randomness with an aqueous solution than with a water solution, just pure water, or pure liquid, I should say. And then for a gas, you'll see these molecules are zooming all over the place. Zoom, zoom, zoom. All right, there's a lot of disorder with your gas molecules zooming around. And notice though you have 2 greater than symbols right here. So the gas is much, much, much more disorderly than the solid and the liquid and the aqueous. So having said that, looking at problems number 1, for each of the following pairs, which substance has the higher position of entropy? Which one is greater disorder at a given temperature? So what do you think? Solid carbon dioxide or gaseous carbon dioxide? I'll pause. You're right, gaseous carbon dioxide. Gases are much more disorderly than solids. Now, what about letter B? When you have nitrogen gas, they're both going to be gases at 1 atmosphere or very, 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 very low pressure, like 1 × 10⁻⁷ atmospheres. Which one do you think has a greater chance at randomness? Well, if you said the one at the lower pressure, right here, you would be correct. This one would have greater chance for disorderly because we have a much smaller pressure. They are much more free to zoom around. They're not being confined as much. Let's go to the next page. All right, it says predict the sign of the entropy change for each of the following process. So keep this in mind. If you have delta S as being positive, that means you have a greater disorder. If you have a delta S being negative, that means becoming more orderly, and that doesn't happen as much. So positive delta S means more disorder, negative delta S means more order. So what's going on here? A solid sugar, which is very orderly, is added to water to form a solution. So this is becoming more disorderly or less disorderly. Hopefully you said more disorderly. We have the aqueous zooming around in a much more disorderly function than a strict solid. How about iodine vaporizes? Iodine vapor condenses in a cold surface to form crystals. So here we have a gas going to a solid. Now, do you think that's very orderly or disorderly for that to happen? you're getting more disorder, excuse me, you're getting more orderly or less disorderly, however you want to look at it, and that kind of goes against nature. So your S is going to be a negative sign here. If you get more neat, it's going to be negative. Okay, so if you pick up your room, your entropy is decreasing, going down. All right, so now what? What can we say about the idea of entropy in the second law of thermodynamics? Well, the second law of thermodynamics says that any spontaneous process, there's always an increase in the entropy of the universe, and you cannot break that law. So for any spontaneous process, you will always have an increased entropy of the universe. And your key word there is universe. I'm sorry, yeah, universe. Okay, so the entropy of the universe is always increasing. So what is the entropy of the universe? It is the system and the surroundings. So normally we just look at the system and we wonder like what's going on with just the system. Well, we got to consider the system and the surroundings. So let's check this out. Let's fill this in here. So according to the second law of thermodynamics, a spontaneous reaction is where you would have the spontaneous process must increase the entropy of the universe. The process is the system and everything else that it surrounds. So the system plus the surroundings will equal the universe. So if you have a negative number, so it's the system itself is getting more orderly and the surroundings are getting more orderly, oh, the universe is getting more orderly too. And is that spontaneous? No way. All right, we said above that the entropy of the universe is always increasing. That's not going to be spontaneous. So if I have a more disorderly system and a more disorderly surroundings, what is my delta S of the universe? Positive. Is it spontaneous? Always. Now, what if the signs are mixed? What will be the delta S of the universe? Well, a plus and a negative number can be either. So I'm going to write depends. All right, it could be positive, it could be negative. What does it depend on? Well, which is bigger, I guess. So it's only spontaneous if your system is bigger than your surroundings. So yes, if the system is greater than the surroundings. So what about the next one? If you have a negative system and a positive surroundings, again, it's going to depend. Depend on what? Well, it's spontaneous this time if only the surroundings is bigger than the system. Okay, so that will all depend. So in a living cell, look what's going on here. In a living cell, large molecules are assembled, I spelled R wrong, from simple ones. So in other words, you're having lots of small little things making one big thing. That's what they're saying here. Is this process consistent with the second law of thermodynamics? And the answer is, well, yeah, a good thing that happens, because otherwise we wouldn't have bodies now, would we? So how can we explain this? Well, the delta S of your system is actually decreasing, all right? But there's another part to it. So if this is spontaneous, and it sure is, then how would you explain that? Well, then otherwise we have to have delta S of the surroundings will have to be bigger for the whole delta S of the universe to be positive. All right, so not only does it be bigger, it has to be bigger and positive for the entropy of the universe to be a positive number. Let's go on to the next page. So actually, I think I'm going to be done with the first one. I have only 14 minutes, or I've used up 14 minutes. So I will stop here, and I will pick up on the next edition of Blank Wall. See you soon.